In the last lesson, we learned how we could identify hydrogen bonds in compounds. And you may have noticed that it's really important to sort of know what the structure of the compound is in order to tell if it can hydrogen bond with itself. Like, for example, ammonia over here, hydrogen bonds really easily with itself. And the reason is because it has that qualification that it has either an N, O, or F attached to a hydrogen. But you remember that's not enough. You also have to have a lone pair on the nitrogen, oxygen, or fluorine in order for that lone pair to be attracted to, well, a hydrogen on another molecule, right? This is the hydrogen bond intermolecular force, and we need that lone pair because that's what the hydrogen is attracted to right there. Now, this compound, ammonium ion, cannot hydrogen bond with itself because even though it has an NH bond, this H when it's being attracted to another nitrogen on another one of these molecules, well, that nitrogen doesn't have a lone pair. So knowing the structure of the compounds is really important. And of course, drawing Lewis structures is the way that we tackle this. However, when you're dealing with larger compounds, these aren't very big, but when you're dealing with larger compounds that are primarily organic compounds, and what I mean by organic compounds are compounds that contain primarily just carbon, hydrogen, nitrogen, and oxygen. If it's just those compounds, there's an easier and simpler way to draw the Lewis structure, and we're going to look at that today. So when you're drawing these Lewis structures, what's usually going on is the more complex organic compounds will have a common name like ethanol or propanone, and they won't require you to know the structure like you would when you take organic chemistry in college, but they'll give you some sort of compressed version of it. Now the problem with these compressed versions is they don't show lone pairs, and we need to know the lone pairs. So how do we turn this into an actual structural formula? Well, it's simply about knowing a couple of things about how carbon, nitrogen, and oxygen bond. Well, carbon up here will need to gain 4 electrons, 1, 2, 3, 4, to be isoelectronic with neon. And because of that, it will always form 4 bonds, always. Nitrogen, of course, needs to gain 1, 2, 3 electrons to be isoelectronic with neon. You remember the term isoelectronic means the same number of electrons. And because of that, it'll always have 3 bonds. Any guess how many bonds oxygen always has? 2. That's exactly right. By the way, what about fluorine? Fluorine always has 1 bond, right? Always, because it needs to gain that 1 electron. So you can see there's a pretty fast way to draw these if you understand that. Now the other thing you need to know is in organic compounds, there's always a carbon backbone. So I usually draw the carbons first. If they say there's 4 carbons, 5 carbons, I'll draw it like that. There are hints within the compressed formula, but you can see in ethanol here, there are 2 carbons. I always draw those first. And then there's an oxygen at the end. And I see that they say there's a hydrogen on that oxygen. They say there's 2 hydrogens on that middle carbon. And they say that there's 3 hydrogens on this first carbon. So easy enough. I've drawn in the structural formula. This one wasn't very hard. I can check it. Does carbon have 4 bonds? 1, 2, 3, 4. Yes, it does. But it also needs to have 8 electrons. And of course it does. 2, 4, 6, 8. This carbon has 1, 2, 3, 4 bonds. And of course it has 8 electrons. So it satisfies the octet rule. The oxygen has 2 bonds, as it should, but its problem is it does not satisfy the octet rule. So how many lone pairs do you believe are on this oxygen? Well, there are 2 lone pairs on this oxygen. Right there and right there. It has 2 bonds, as it should, but it needs to have 8 electrons, so it has 2 lone pairs. Whereas look at propanone down here. If I were to look at its carbon backbone, it seems to have 3 carbons. Now, I have a little bit of confusion about the way they draw it. Do they mean the O is in the middle of those carbons? Or do they mean that the O is somehow like attached to that middle one in that way? Well, if we explore this a little bit, clearly the carbon on the end has 3 hydrogens. This oxygen doesn't seem to have anything. That carbon doesn't seem to have anything. But this one at the end seems to have 3 hydrogens. Now, if I've drawn in all the atoms and I can't add more hydrogens, let's look at problems. Well, the carbons on the ends have 4 bonds and they have satisfied octets. But this carbon only has 2 and does not have a satisfied octet. And that oxygen has 2 bonds, which is good, but it doesn't have a satisfied octet. Well, I could put the 2 lone pairs on there, and oxygen would have its required 2 bonds and 8 electrons. This carbon, though, I can't add 2 lone pairs because that wouldn't give me 4 bonds. I need 4 bonds. Well, maybe there's a double bond. But if I draw a double bond this way, you can see that now this carbon has 5 bonds. Let me get my erasing tool out. I like how slowly this erases. All right. If I draw the double bond this way, you can see now oxygen has 3 bonds. And I would even need to do another one because the carbon still doesn't have 4. I'd have to do that. And you can see that the oxygen has too many. It becomes a mess. So I think what they mean here is the oxygen is up on the carbon because the ones on the end, of course, have the 3 hydrogens. And the one, they got to do this one too. And you can see the end ones have their 4 bonds and 8 electrons. This one does not have 4 bonds. I don't want to do a lone pair because that won't give me 4 bonds. But maybe there's a double bond. Now we know we can't go to the left because that would give this one over here. That would give this one over here a double bond, and that would be 5 bonds. That one doesn't work. It can't go this way because that would be 5 bonds on this one. So let's try going up to the oxygen. Now this carbon has 1, 2, 3, 4 bonds, and the oxygen has its required 2 bonds. Now are we done? No. We need a lone pair on here to give oxygen that satisfied octet. So this one did not turn out to be right, and this one turned out to be pretty good. And our understanding of 4, 3, and 2 bonds on these atoms helps us quickly clarify what's going on. Now since we're here, let's see what type of intermolecular forces could be between an ethanol molecule and another ethanol molecule. Well, the question is, could it hydrogen bond? Well, it has an O attached to an H, and it has a lone pair. Yes, it can do that. Anything that hydrogen bonds also has dipole-dipole forces, because a dipole-dipole force, or hydrogen bond, is just a strong dipole-dipole force. Does it have London dispersion forces? Yes. All atoms that have electrons, that means all molecules in the entire world, have London dispersion forces. So this one will have all 3. Let's go down and look at propanone. Well, can propanone hydrogen bond? It has an O and it has an H, but no, it cannot hydrogen bond because the O needs to be attached to the H. Yes, this has a lone pair, but it doesn't have an O attached to an H, so it cannot hydrogen bond. Can it do London dispersion forces? Yes, all molecules that have electrons have London dispersion forces. Can it dipole-dipole? Well, I don't know. Since it didn't hydrogen bond, we need to ask ourselves, is it polar? Because if it's polar, then it can do dipole-dipole attractions with another molecule like it. Determining if a compound is polar in a bigger molecule might seem like a huge endeavor. Let me get a different color pen here. It might seem like a huge endeavor because you might think, oh, look at how many dipoles I need to draw on every single bond. But you remember, there is no dipole here between carbon and hydrogen. There's no dipole because it has very similar electronegativities. So this part we don't need to worry about, and the end part we don't need to worry about. We just need to worry about the middle. So you know that if I were to draw around this carbon, if I were going to figure out its polarity, I need to draw a better shape because I don't think it's T-shaped. So around this thing, how many electron groups do you see around this central carbon? I see 3 different directions. And so it's going to be a shape that's more trigonal planar, which means a better way to draw this thing would be, and I'm not going to do the whole chain going off that way, but the bond angles would be 120 degrees. It would be trigonal planar about this central atom. So we can tell the shape around one central carbon. Now, there is no bond dipole between these carbons, agreed? They have the same electronegativity, so I shouldn't be drawing a bond dipole. But there is a bond dipole being pulled towards oxygen. So that means there is no offsetting other dipole, and yes, this thing will be polar. Therefore, yes, it has dipole-dipole interactions. So that's how in a larger molecule we draw it quickly and figure out if it's polar. Let's try another one. I want you to draw the Lewis structure for propyne here. And then I want you to decide what intermolecular forces it would have in it. All right, so here's how I'm going to do it. I'm going to draw the carbon backbone first. That's 3 carbons. I'm going to draw the hydrogens I'm confident of. I know that one has 3. This one doesn't seem to have any, and the one at the end seems to have 1. So we can't draw any more hydrogens, that's it. But the carbon on the left, it's good to go. It has 4 bonds, as carbon always has 4 bonds. But the carbon here only has 2, and the carbon there only has 2. Now I can't add more hydrogens, so you know we're going to have to add double bonds. I don't want to add my double bond going this way because that would give this carbon 5. So let's try between the 2 that seem to need more. Now this carbon has 1, 2, 3 bonds. That one has 1, 2, 3 bonds. Things are going pretty well, but it needs 4, so it's probably going to be a triple bond. 1, 2, 3, 4, yep. 1, 2, 3, 4, yep. And all the octets are satisfied. We've done a good job. That's what propyne looks like. Well, let's figure a few things out here. What kind of intermolecular forces can it have? Can it have hydrogen bonding? Well, no. There's no OH, NH, or HF. That's out. Can it do dipole-dipole interactions? Well, in order to do that, it's got to be polar. So if I look at this compound, I don't have to draw bond dipoles between carbon and hydrogen or carbon and carbon. I don't see any bond dipoles, so it can't be polar. There are no dipole-dipole interactions between this and another molecule like it. Does that mean that this thing will have no attraction to another propyne? No. It will have an attraction because it has London dispersion forces. All compounds have London dispersion forces if they have electrons, and all compounds have electrons. So its intermolecular force between it and another molecule will be a London dispersion force. It's going to be pretty weak. Oh, while we're here, incidentally, let's try this. What I want you to do is write down, what do you think the bond angle will be at carbon 1? What do you think the bond angle will be at carbon 2? And of course, what shapes will it be around those? Well, number 1 will be tetrahedral because there are 4 electron groups. It will have ideal bond angles of 109.5 degrees. Number 2 will be linear because there are only 2 electron groups, and the bond angles will be ideal, and they'll be 180 degrees. So we can find the angles around little parts of molecules like that. All right, let's do one more. I want you to draw the Lewis structure for formamide, and then decide what intermolecular forces does it have. Okay, well, I'm going to start with the carbon backbone. Ooh, I got one of those O's where I'm not sure if the O is here or if the O is maybe on the carbon. So let's try it out. Well, if I'm up here and I know that I have 3 hydrogens, like that, I'm going to draw them small so it doesn't bump into that one. This carbon seems to have nothing, the O seems to have nothing, and the N seems to have an H and an H. Well, I'm super comfortable with the nitrogen because it already has 3 bonds, because all nitrogens have 3 bonds. And I can add a lone pair to satisfy its octet. The oxygen has 2 bonds, and all oxygens should have 2 bonds. And I can add a lone pair to satisfy its octet. I'm liking how this is going. I get to carbon, but carbon is meant to have 4 bonds, and I can't add lone pairs because that won't give me 4 bonds. Can I do a double bond maybe to the left? No, because that would give me 5 bonds on that. Can I do a double bond maybe to the right? No, because now that gives me O having 3 bonds. That's out. It's not going to work. It must mean that the O is on top of the carbon. All right, we know the end has 3 hydrogens. We know this end has 2 hydrogens. As I said last time, it has 3 bonds, so that's fantastic because it's a nitrogen. And I can give it a lone pair to satisfy its octet. Well, let's look at the middle carbon. It only has 3 bonds. It needs 4, and you can see what's going to happen because the O also needs another one because it needs 2, so I draw a double bond. Now, are we done? No, because carbon or oxygen also needs a satisfied octet, so it will have 2 lone pairs. There we go. That's what it's going to look like. Let's figure out what intermolecular forces it can have. Can it hydrogen bond with itself? Well, this oxygen does not have a hydrogen attached to it. Ooh, this oxygen does not have a hydrogen attached to it. But this nitrogen does have a hydrogen attached to it, and it has a lone pair, so yes, it can. By the way, a little aside, you might wonder, this hydrogen right here, when it's attracted through a hydrogen bond to another molecule, would it be the N or the O, since it has both? Which lone pair would hydrogen bond with this? And the answer is both. But I suspect that the oxygen is going to be slightly more negative, so I think the oxygen would tend to do it more. But this compound, I would expect to have a very high boiling point because it has so many places it can hydrogen bond. Okay, anyway, can it do dipole-dipole interactions? Yes. Anything that hydrogen bonds will do dipole-dipole interactions because there will be a center that is polar. There's probably more than one on this molecule, but let's just prove it around this nitrogen. This nitrogen has 1, 2, 3, 4 electron groups, therefore it's what shape? It's tetrahedral. Its bond angles are 109.5. Are these bond angles going to be ideal? No. They're going to be a little bit less than that because of the lone pair. So N is going to look like this. We're going to have the lone pair like that. I'm going to have the carbon chain. Let's say the carbon chain right here. I'm not going to draw the rest of it. We're going to have hydrogen and hydrogen. And these bond dipoles do not offset. Nitrogen is slightly more electronegative than carbon. It's more electronegative than hydrogen. And you can see there will be a net dipole moment going up. There definitely will be a negative and positive side. Hence, it is polar and must have dipole-dipole interactions. But all compounds that have hydrogen bonds have dipole-dipole interactions because this is just really polar, right? Does it have London dispersion forces? Yes. All compounds with electrons have London dispersion forces. So that's how we tackle it. That's how we identify intermolecular forces in a compound, and that's how we draw structures quickly.